Okay, so today is going to be section 2 and really the third part of it. So the first part, we just talked about using Newton's laws. Then we went into apparent weight for the second part of that. And then today, we're going to be talking about drag force and terminal velocity. Okay. So drag force, terminal velocity, they're both related to objects in free fall, although drag force can also certainly apply on an object moving horizontally, right? So drag force, we're going to kind of use somewhat interchangeably with air resistance. Um, so let's think about this for a second. Drag force is really the force exerted by an object moving through the air. It's actually the force that the air exerts on the object. Okay, so if I have, let's imagine like a semi. I'm going to make this one of those really ugly stub nose semis. Yeah. Yeah, I don't like them that much. I think, or at least I think they're ugly. But as that object is moving, horizontally, it's colliding with multiple particles in the air. And these these particles, so the air particles, as they're moving around, as they're bouncing into objects, they're exerting a force on it, right? Now, actually, all objects get a force of those particles in the air exerted on them. Okay, even a stationary object, so like even me as I'm standing here, has a force being exerted on me due to these air particles. Okay, so, but the thing is these forces are kind of symmetrical.
Yeah.
Right? So you don't really feel it. Okay? It's kind of pushing around on you on all sides. So the net force really kind of balances out. Now, if you imagine something like it's actually kind of interesting. There's actually quite a bit of pressure due to the air, and you can see like the reason a soda bottle collapses when you like suck the air out of it is because when you take the air out of it from the inside, the air on the outside is actually collapsing it.
That's pretty cool.
So yeah, there is actually a pretty big force there. So anyway, drag force is the force that these air particles exert on a moving object. So not only are they exerting this force, as this object is moving, it has to push them out of the way, right? So we have all these particles colliding. They do have some mass to them, which is going to transfer energy and all that stuff. So as this is moving, these are colliding, imparting energy onto the semi. Obviously, we talked earlier how the shape of the object is going to influence the drag force. So a sports car that's very, very low profile and aerodynamic is still going to collide, although if it's lower to the ground, it's going to impact fewer air particles, and due to the aerodynamics, they're going to glide off of them, right? That angle when they hit less. So anyway, drag force is fairly straightforward. We're going to talk about terminal velocity today. Okay. Actually, first, one more thing I want to mention about drag force. Drag force is kind of like friction in that it always opposes the motion of the object. Okay, so if you have a car and it's moving that way, drag force. So if this is its velocity, drag force is always gonna act in the opposite direction, right? If it turns around and goes back the other direction, drag force is going to act that way, right? It's always going to oppose the direction of the velocity. Okay? So it always opposes the direction of velocity. So there's a few things that drag force depends on. So what do you think is going to influence the amount of drag force on an object?
Surface area.
Okay. So surface area. Anything else?
Would the speed affect it?
Speed is going to affect it, yes.
Aerodynamics.
Sure. We'll call that shape. Shape of the object, because the shape is going to affect the overall aerodynamics. And actually, surface area may not be the best description, because the surface area of this car is like the entire surface area, right? More specifically, it's cross-sectional area, okay? Because a car that has the exact same shape is going to have a similar aerodynamic kind of property, but if it's small, just kind of completely smaller, right? To where that cross-sectional area is less, it's going to have less air impacting it. It's going to have less drag force. Okay. So cross-sectional area, speed, shape. Anything else that would affect drag force?
Would the mass of the object affect it?
The mass of the object would play a role in kind of the big picture of how its motion, but it's not going to affect the drag force that the air is exerting on it. Okay. The last thing that's really going to affect it is the properties of the fluid. So the fluid that it's actually moving through. Okay. And there's actually two kind of properties that matter, and that is viscosity and temperature. Okay. So do you know what viscosity is?
It's a resistance to flow, right?
Yeah. So different fluids have different viscosities, based on its composition, and temperature also impacts that. So air is going to have a certain viscosity, probably might change very, very minutely at different altitudes. Temperature is also going to affect that. So this drag force doesn't have to necessarily be air resistance, although that's a really common one. It could be an object moving through a fluid, imagine like a submarine or something like that. So water is going to have very different properties than air, right? That resistance would be a lot more. So We've got properties of the object that's moving, cross-sectional area, speed, shape, and then properties of the fluid. Okay, makes sense. I think I can remember this. So the actual formula for drag force is, the notation we use is F sub D. And this isn't something I expect you to remember. We're actually not going to mess with this actual formula a lot, but just so you can kind of see some of the relationships. It's 1/2 PV squared. And I believe it's an A. So this is drag force equals 1/2. This is the density of the fluid. This is speed of the object. Okay. This is actually the drag coefficient. Okay. And then this is the cross-sectional area. Okay, so you can kind of see there the things that it's all dependent on. The thing that I wanted to point out with bringing this formula up, not that you have to memorize it or even that we're going to use it to calculate drag force at all, but that it's dependent on speed squared. Okay, so what that means is as speed increases, drag force actually increases quadratically. Okay, so it's not a linear relationship. Drag force increases based on the square of the speed. Okay, so actually, as speed, if you think about it, as speed doubles, drag force is going to quadruple. As speed triples, your drag force is going to increase by a factor of 9, right? Which makes sense. I mean, we have cars that have, hundreds of horsepower that can accelerate very, very rapidly at low speeds. But yet by the time they get up above 100 miles an hour, at some point they're topping out because their horsepower is equal and opposite. I mean, there's so much drag force acting on them that they can't overcome it. So, makes sense. Anyway, just wanted to show you that. So the next thing that we're going to take a look at is terminal velocity. Okay. So terminal velocity is the constant, is the constant speed that a falling object reaches. So if you imagine, say, a tennis ball falling, or any falling object. Let's say you drop a rock out of an airplane. Okay, imagine a small little rock. Okay, so we've got our our falling rock, and it's traveling somewhat slowly at first, but it's accelerating, and it's traveling faster and faster and faster. Okay, up here, when the velocity is very small, drag force is also very small.
Yeah.
Okay, but so let me back up 1 second. When it's falling here, if we assume it's in free fall, right, the only force acting on it is the force due to gravity.
So it would never stop getting faster. Right. If there's only gravity.
Well, so it's accelerating at 9.8 meters per second. It's not necessarily never going to stop getting faster. Because it accelerates, it's going faster. Well, what happens? So in reality, there's actually going to be a tiny amount of air resistance here, but for all intents and purposes, it's negligible. Okay? But as it accelerates, the velocity increases, right?
Mm-hmm.
So we still have F sub g, but now drag is increasing. I'm gonna zoom in a little bit here. Okay. So my velocity is increased, that drag force is increasing. So as this object accelerates, well, now the velocity is increasing even more. F sub g is staying the same, but the drag force is going to keep increasing as it accelerates. Eventually, that drag force is going to equal F sub g, and those are going to balance out. Okay. Once that happens, and those are equal and opposite, okay, then the net force is zero, so the acceleration equals zero at that point. Okay, and that's where it's reached terminal velocity. Okay, does that kind of make sense?
Yeah.
It starts out with almost no drag force, but as that speed increases, we just looked at that formula and how the drag force increases based on the square of speed. So the drag force is going to keep increasing as it speeds up. Eventually, as soon as it reaches equal and opposite to F sub g, then acceleration stops. Okay, and that's where it reaches terminal velocity. Okay, so we should probably write out a definition for that. So for terminal velocity, it is the constant velocity of a falling object. When the drag force equals its weight force. Okay, does that make sense?
Yeah.
All right, and then just a couple things to note about that. When you have an object in terminal velocity, the net force, of course, is zero, and also the acceleration is zero. Yep. Okay, and different objects are going to hit terminal velocity at different times and at different speeds. There's not a single value for terminal velocity, right? If we imagine this rock falling, depending on the aerodynamic properties of a rock, that drag force is going to behave differently. If we have a skydiver jump out of the plane, okay, if he dives headlong, they're gonna fall pretty rapidly. I believe, interestingly enough, I believe that terminal velocity for a human, people have actually studied this. I want to say it ranges from if you're in a straight upright position, arms and legs tucked in. I believe you can go up to 100 and I'm not sure if it's in the 120 range or 160. I'll look that up here in a second. And then, of course, if you change orientation and you go, all horizontal, spread out, then, of course, your terminal velocity is going to change. You changed your surface area, right? So the drag force then is going to increase, and your terminal velocity would be a lot less. I want to say this is maybe 70 miles an hour. Again, I'll look those up here in just a second. And then, of course, if you have a parachute on, your terminal velocity is going to be even less, right? Because you've got a lot more surface area, a lot more air resistance. I'm going to look those up here in just a second. Okay. So we talked there a little bit about terminal velocity. Hopefully that makes sense. just for the video, we looked up, and the terminal velocity of a human and the belly down position is about 120 miles per hour. Here, I need to zoom this out.
Science.
Terminal velocity of a human, if they're belly down, 120 miles per hour, and if they're like in the head first position, about 150 to 180 miles per hour. Real quick, let's look at the terminal velocity of some common objects, just to give you guys some ideas for just kind of normal objects. A table tennis ball has a terminal velocity of only 9 meters per second. A basketball is going to have a terminal velocity of 20 meters per second. And a baseball is going to have a terminal velocity of 42 meters per second. Okay? And this kind of goes back, you remember at the beginning of the year we talked about this kind of misconception that all objects would fall at the same rate in a vacuum, okay? Because the acceleration would be a constant, 9.80 meters per second squared, no matter what their mass was. Air is kind of the reason that we don't always see that play out identically. Reason being, so if we have a ball, actually if we have two balls of equal size, shape, aerodynamic properties, right, going to be exactly the same. Well, let's say this one is 5 kilograms and this one is 10 kilograms, okay? In a vacuum, they would fall at exactly the same rate, okay? Exact same, 9.80 meters per second squared would be their acceleration. On Earth, though, in the atmosphere, if these were both dropped from a very, very high altitude out of a plane, the air resistance would be the same on them, okay? At any given velocity, the drag force would be equal. Does that make sense? Same aerodynamic properties, same speeds, but F sub g on this one is going to be twice what this one is. Okay. So in a vacuum, even though the F sub g is greater because of the greater mass, same acceleration, but due to air resistance is going to be a smaller percentage of this one than that. So you can think kind of very, very light objects that have a big surface area are going to have a much lower terminal velocity.
Like paper.
Right. So ironically though, yeah, if you had a piece of paper, this would just be weird to see, but if you had a piece of paper in a vacuum, it would fall at the same rate as a rock.
I like that.
Yeah, just seems